Perfect. Good afternoon, everyone. It's a pleasure to have you here for our fifth Disaster Mobility Data Network. Over the last meetings, we have shared use cases, policy insights, latest data trends, data sources, and challenges around the use of mobility data. The agenda for today is the following. First, we're going to have Boyeong Hong talk about the exposure density, or the role of urban analytics to fight neighborhood gaps, followed by the presentation from Enrico Ubaldi on Mobilkit Disaster Risk Management Toolkit. Before we begin, I'd just like to make some comments on the housekeeping. During the presentation, please write any questions in the chat and we will address them at the end of each presentation. We also have time at the end for further discussion. Please feel free to come off mute and contribute during the Q&A at the end. Remember that all our meetings are recorded and uploaded to the CrisisReady YouTube channel, so if you missed any of the past meetings, you can see them there. Without further ado, I would like to welcome our first speaker. Boyeong is a visiting assistant professor at the Urban Planning Program at Columbia Graduate School of Architecture, Planning and Preservation. She's also an associate researcher scholar at the NYU Marin Institute of Urban Management in the Civic Analytics program. Her research and teaching interests are motivated on how urban informatics and urban tech, big data, machine learning, and urban science expertise to real-world problems with respect to urban planning and operations, ultimately aiming at equitable city service allocations. As an interdisciplinary expert, she joined the Urban Design Forum as a Forefront Fellow and received the William H. White Award for the American Planning Association at NYU Metro Chapter. She received a PhD in Civil and Urban Engineering, majoring in Urban Informatics from NYU, and holds a Master in Applied Urban Science and Informatics from NYU Center for Urban Science and Progress. As a capstone advisor, she encouraged students to utilize various data sources, resources, and analytic skills to understand and quantify the urban phenomena at scale. Potential domain interests include, but are not limited to, urban mobility, city operations, resilience, and public health. Please, Bo, the screen is yours.
Thank you, Andy, for a great introduction. So hello, everyone. First of all, thank you for your time and thank you for your time to join this session. Again, my name is Bo, just call me Bo, and I'm currently an associate research scholar at NYU Marin Institute of Urban Management. And my research work basically for today's presentation has been done within NYU Marin Institute of Urban Management. Although it's over Zoom, I'm very excited to be here today to give this talk, the role of urban analytics to fight neighborhood gaps. So today, I'd like to focus on measuring neighborhood gaps at the granular level based on large-scale mobility data. So one of the examples, this video shows human mobility in greater Houston area during Hurricane Harvey in Texas, 2017. And before the hurricane, we can see clear patterns of highways, commuting patterns, and normal activities in and out of downtowns. But when hurricane hit Houston on August 26th, basically, normal patterns of the city suddenly disappear, and there were way less and sparse activities across the city. So this data with a proper computation represents neighborhood level response and evacuation patterns. So it can be directly used for measuring hurricane damage and resiliency associated with neighborhood climate gaps. So we're probably now in the next phase of urban planning, and large scale data in urban analytics can tell a story about urban dynamics and neighborhood gaps with respect to either everyday normal life or urban crisis. I'd like to mainly talk about a very timely research about the COVID-19 pandemic. Briefly, this research used a large-scale geotech mobility data and machine learning technique to identify significant neighborhood disparities in neighborhood responses to the COVID-19 pandemic, which is very closely related to varying public health outcomes. So look at those two images. I mapped a very small random subset of smartphone ping data without any computation. The left one is before COVID, and the right one is 2 days after the stay-at-home order declaration. So it clearly shows a significant change of mobility and activity levels in Astoria, one of neighborhoods in New York City. Despite universal policy implementation, the impact of and response to the stay-at-home order is not uniform across neighborhoods, and this has contributed to further disparities in risk of infection. Also, there have been disproportionate public health impacts on vulnerable communities in terms of COVID cases and death, which may or may not be closely related to social distancing behaviors. We have had a hunch, but it has not been proved. Some previous studies often focus on core spatial resolutions, such as county or state level, because of data availability or computational constraints. However, social distancing behavior change and public health interventions, it should be measured and examined at the scale of individual neighborhoods. We know there is a significant neighborhood gap, and understanding this gap at scale, it would provide critical insights into the design and implementation of more effective and equitable public health policy. So this research project aims at developing a method to identify and measure neighborhood gaps with respect to social distancing and public health outcomes, focusing on the New York City metropolitan area. This study firstly quantify neighborhood activity at higher spatial and temporal resolutions using larger scale location data mining. Then this study tests whether and to what extent behavior responses to social distancing policies vary with neighborhood characteristics based on computational modeling. The main data resource for this study is an anonymized large-scale geotext smartphone data provided by VanPath, which is one of the third-party data providers. It's basically smartphone ping information collected from more than 200 different applications. But of course, data doesn't reveal specific app information. The initial data size was 22 terabytes, and this study only focuses on the period from February through April 2020, so covering before, during, and after the stay-at-home order. After filtering data based on the New York City specific bounding box and removing non-valid users, the data covers approximately 13 million unique devices with 23 million pings. Then in order to avoid tracking of individual devices, all data points were spatially and temporally aggregated at 250 meter grid cell and 5-minute interval. Those aggregated data points were integrated with land use rasterization information to classify individual pings into 4 different groups of neighborhood activities: residential activities, non-residential activities, outdoor activities, and vehicular activities. Many COVID-19 related studies have focused on the relationship between COVID-19 infections and population size or population density. Most research are based on census population data, which does not represent actual activity density in the neighborhoods due to its static nature. So this study defined and developed an exposure density concept. Exposure density is a measure of localized activity occurring in areas that can be associated with an increased risk of exposure to other that may be infected. So basic assumption is that people who change their behavior dramatically and stay home, they have less probability of close contact with infected people. So this exposure density concept mainly takes into account non-residential and outdoor activities. Mathematically and computationally, this exposure density measures the number of unique devices in a given geographical and temporal unit by land use type. So for the first step of measuring exposure density for this study, we computed the hourly number of unique devices in each 250 meter grid cell and the corresponding land use category based on the raster cell. So this time series plot in the slide, it shows the citywide non-residential and outdoor activity change over the time, so from mid-February through the end of April last year. So overall, we observed approximately 20% decrease in neighborhood activities outside of residential buildings after the stay-at-home order. This slide shows a descriptive picture of neighborhood activity change over the time period in the city based on the exposure density metric. So firstly, time series plots describe average neighborhood activity by land use type by 250 meter grid cell before and after the stay-at-home order. So top two plots are city-wide average neighborhood activity volume change, and bottom two graphs are city-wide average neighborhood activity proportion change. So red lines are residential activities, green is outdoor activities, orange is non-residential activities, including offices or commercial spaces, and purple lines show vehicular activities on the highways and the major road without pedestrian access. As you can see here, after the stay-at-home order, overall neighborhood activity volumes decreased, and weekday kind of 9 to 5 patterns have disappeared. So for the activity proportions, residential activity proportion has been dramatically increased, while other activity types decrease. The right map shows a spatial pattern of the exposure density change by 250 meter grid cell based on the activity volume change of non-residential and outdoor activities during the two time periods. So 2 weeks period before the COVID and after the stay-at-home order. Higher density neighborhoods, including most of Manhattan, downtown Brooklyn, Long Island City, they decrease in exposure density a lot, but outer borough neighborhoods show rather increasing neighborhood activity levels after the stay-at-home order. To understand disparities in exposure density and behavior responses to social distancing mandates across different neighborhoods, we applied an unsupervised machine learning clustering algorithm based on a pre-post comparative analysis. We extracted exposure density subsets for two weeks period. So the pre-impact period, February 16th through February 29th, and the post-impact period, March 29th through April 11th, to measure changes in exposure density before and after the stay-at-home order. In order to take into account both the absolute change in activity volume and the change in the proportion of activity type, a total of 6 input variables were created for the zip code neighborhood clustering analysis. So neighborhoods are classified into 5 different groups. So this slide visualizes the spatial patterns of the clustering output and time series of neighborhood activity and where that activity is occurring by land use type. So red is again residential, orange is non-residential, green is outdoor activities. So group number 1 and 2, they are primarily located in Manhattan and downtown Brooklyn, and they represent substantial changes in exposure density after the stay-at-home order. The average activity volume change for group number 1 and group number 2 is minus 57% and minus 34%. And it means that these 2 neighborhood groups experience significant declines in normal activity levels across all land use types during the pandemic. Group number 3, there are like 43 zip code neighborhoods. So these neighborhoods show a 19% decrease in exposure density. Although I see a marked outflow of residents, these neighborhoods maintain a stable proportion of activity between the different land uses. This indicates that residents who remained in these communities, they largely maintain irregular behavior patterns. Communities in the group number 4 cluster, they have stable activity patterns over time. However, those neighborhoods did not see a significant outmover population. So we labeled stable group for those communities. And lastly, in comparison to other clusters, group number 5 neighborhoods, they demonstrate a 20% increase in local activity volume for residential activities and a 7% increase in outdoor activities. In addition to increasing overall neighborhood activity volume, residents staying in these neighborhoods are found to shift activity to residential buildings almost by 10% and away from non-residential and outdoor activities by 6%. While non-residential activities are found to decrease as a proportion of these 3 activity types, the increase in the overall volume of activities leads to a net increase in exposure density compared to the pre-COVID period. And this slide shows descriptive statistics of neighborhood features for each group, and it reveals very distinct neighborhood profiles based on changes in exposure density over time. So for example, most neighborhood in group number 1 and group number 2, overflow groups, have a higher percentage of younger non-Hispanic white residents, relatively smaller average household size, and higher incomes and education attainment. Group number 3, stable outflow communities, they have higher proportion of racial and ethnic minorities and lower median incomes, as well as significantly higher proportions of renter households and those without health insurance. Additionally, a greater percentage of employees in these neighborhoods, they work in retail services and healthcare support occupations or essential businesses that were not required to close during the outbreak. In group number 4, labeled the stable group, it comprised socioeconomically vulnerable populations in a high proportion of racial minorities, the second lowest median income, large average household size, high unemployment rate, lower education attainment, and a large share of healthcare support workers. Also, we found that the relatively modest change in exposure density in the stable groups is associated with a significantly higher infection rates. So in particular, the stable neighborhood group, so group number 4, it shows the highest case rate, death rate, and positivity rate in the city. In group number 5, outer borough communities. So this group has the highest proportion of elderly population, the largest household size, moderate incomes, a relatively lower percentage of racial and ethnic minorities, and a significantly higher home ownership rate. So this indicates that activity in these neighborhoods where housing density is the lowest in the city, it became more localized compared to the pre-COVID. So the effect of this local activity was, an increase compared to the pre-COVID level, and the probability of coming in contact with others outside of the household or family unit. So as a result, group 5 experienced the second highest infection rate, even though they have the relatively low built environment and population density compared to other neighborhoods. And lastly, I evaluated the effect of neighborhood change and COVID-19 infection rates for the neighborhoods. So I firstly developed log transport bivariate regression models based on relationship between exposure density change and 4 different infection rate metrics. So case rate, death rate, positivity rate, and fatality rate. So there are clear relationship between exposure density and case rate, death rate, and positivity rate, but as expected, not being a statistically significant determinant of mortality rate. So based on the simple modeling, we found that if all neighborhoods in the city reduce exposure density by 10%, as compared to normal activity level prior to the stay-at-home order, approximately 29,000 COVID cases could have been avoided, and almost 3,000 lives could be saved through the end of June 2020 last year. This research also developed multivariate log transform regression models to identify any significant effects of exposure density on infection risk, controlling for neighborhood characteristics. So we combined both outflow cluster groups, like group number 1 and number 2, and used a stable neighborhood group, group number 4, as a reference case for dummy variables. So after accounting for neighborhood covariates, we continued to observe statistically significant coefficients for the exposure density variables. So neighborhoods that reduced exposure density show a 44% lower positivity rate compared to the reference group. For outflow neighborhoods that maintain the distribution of activities across land use types, the output shows 23% lower positivity rate. These findings provide additional empirical kind of evidence for the effectiveness of social distancing as a non-medical intervention strategy to reduce COVID-19 spread. And it reinforces that proactive neighborhood behavior change, it can help to prevent transmission of the virus during the pandemic. In terms of sociodemographic features, as importantly, race and ethnicity, age group, and socioeconomic status are found to have statistically significant effects on neighborhood infection rates and disease outcomes. Communities with larger proportions of minority and lower income populations are more likely to be at risk for virus transmission. So to recap, this research project analyzed large-scale geolocation data and granular land use classifications to measure high spatial temporal neighborhood activity level and exposure density. The findings from this research demonstrate distinct patterns of activity before and after the stay-at-home order across neighborhoods in New York City. These neighborhood patterns are clustered into 5 different groups, each exhibiting statistically significant differences in socioeconomic, demographic, and built environment characteristics. The variation in exposure density has a direct and measurable impact on the risk of infection. The communities hardest hit by the virus were in the stable neighborhoods, where residents face multiple challenges and risk factors. So these communities have the largest proportion of racial minority, among the lowest median incomes, and the lowest rate of health insurance coverage. These compound risks resulted in these vulnerable communities facing the burden of the highest rate of infections, death rate, and positivity rate in the city during the study period. So even though the universal policy program has been implemented to all neighborhoods, responses to this policy were totally different across neighborhoods, depending on their circumstances, probably social norms and other external factors. This larger scale data analytics research demonstrates a clear neighborhood social distancing gaps, resulting in significant neighborhood public health gaps. So this novel research method and findings have clear contributions. The first, developed a computational approach to measure exposure density at high spatial and temporal resolution is scalable. And second, this research provides a foundational finding of neighborhood gaps. This research demonstrates the significant disparities in behavior responses to social distancing and health outcomes for racial and ethnic minorities and lower income households. And these objective findings contribute to theorize neighborhood inequalities and gaps regarding different urban phenomena. And lastly, this study contributes to suggest a tool for the design and evaluation of equitable and targeted public health interventions based on hyperlocal exposure density measurements and measured neighborhood gaps. So instead of applying a universal policy program, the city government or state government or federal governments, they can adjust or add on their policy program after quantifying neighborhood disparities. So as this diagram shows, targeted and localized social distancing policy interventions, it would break or at least weaken the linkage between neighborhood social demographic disparities and social distancing gap, or social distancing gaps and public health gaps. So this is it for this presentation. So thank you for listening.
Thank you very much for your presentation, Bo. Is there any questions from the audience? By the way, have you shared this research with any public officials in New York City?
Not from my side, but actually one of our collaborator is in NYU Medical School. So she actually provided this research to I think the Department of the Health in the city.
Oh, great. Okay, while the audience thinks on other questions that we could address at the end, let's follow with Enrico's presentation. So if you could stop sharing your screen and then we'll go. Meanwhile, I'll give the introduction to Enrico. He's a data science and artificial intelligence researcher at MindEarth. He has a PhD in theoretical physics, where he studied the evolution of complex systems, such as social networks and dynamical processes, in large populations of agents. He then started working on mobility data to inform models of urban development and measure accessibility metrics. He joined MindEarth to develop data analysis pipelines to detect shifts in human mobility under major perturbation, use remote sensing and street-level photographic surveys to infer socioeconomic indicators at high resolution. In a joint collaboration with the World Bank Global Facility for Disaster Recovery, the Reduction and Recovery, he developed Mobilkit, a Python toolkit to measure the response of large population to extreme events. It's actually currently used to characterize disaster response in different worldwide scenarios. Enrico, the screen is yours. Thank you very much.
Okay, thank you very much, Andrea. And I will share my presentation.
Enrico, I can't hear you.
Enrico, I think you're in mute.
Yeah, can you hear me now?
Yes, now we can hear you.
So it's strange because as soon as I share the tab, the audio disappears. Ah, okay. I don't have to share the audio, so sorry. Uh, can you hear me now, even though if I'm presenting?
Yes.
Okay, sorry about that. So very quickly, I will just go through the first slide. So again, I'm Enrico from Mindert, and I'm presenting the Mobilkit utility for disaster risk management. As we saw from the Bo presentation, mobility data are fundamental in planning and following disaster and risk management situations, mainly because thanks to the position data, we can map risk exposure during the day, follow the recovery processes, etc. And this has historically been done with quantitative records that, however, are hard to access and feature low resolution at the antenna level. The advent of GPS data instead allowed to monitor the movements of the population on a finer scale, especially to unlock the possibility to characterize routing choices, displacement, and so they were able to assist also, for example, transportation planning, and also, of course, to follow in more detail both temporal and spatial the population movements after a disaster, so the response to a disaster and a recovery of the population from it. Mainly because the GPS data are not event driven, but are also passively collected. There are many tools to analyze this data at the user level or at a small population level. However, the disaster management requires some functions and some tools that are not implemented there. So besides the accurate dynamical description of the population, disaster response management also requires a quick measure of the response, so being able to analyze data quite fast. Today we will show you how Mobilkit can be used in all the steps of the disaster management, basically from the mitigation phase with the land use and risk exposure mapping to the preparedness to see how shelters, for example, after an earthquake are used, measure the displacement after a disaster, and then population relocation. Another point that motivated the development of Mobilkit is the size of the dataset. So this is the usual dataset that you start from. So you have a user identifier, a timestamp, the coordinates, and then the accuracy of the registered position. And this data can scale pretty quickly to thousands, if not millions of users, and feature billion of rows. Okay, so we have to cope with a sample size that is getting bigger. When we have a large region of interest to study, we need the temporal requirements, the computational requirement to scale well with the amount of data, especially to characterize the response to a given event. And also we need to cope with the fluctuation in the number of users and recorded positions that we have in the data. It is not at all unfamiliar or unusual to see this kind of fluctuation in the number of users within a dataset of GPS data. And also we wanted to develop Mobilkit to provide an easy-to-use programming interface, and easy-to-use high-level language or functionalities that also the non-technical, non-expert users could use in the daily analysis of data. So the implementation of Mobilkit is modular. We, of course, start with a module to load and import and perform some pre-processing on the data. So, for example, to localize the timestamp of the data and dump or reload the previously analyzed dataset. There is then a statistical module where we can compute some statistics per users. We will show that later. If we add some auxiliary data like a tessellation, a shape file, for example, or some census figures, we can also see the spatial distribution of these events, the homework origin destination matrices, for example, and compare them to census figures. There are two additional modules. One is the temporal one that deals with everything that has to do with the activity profiles, number of people being at a given location in a given time, and some more function devoted to the characterization of shift changes or let's say drift from the usual behavior of people in how they allocate venue visits or in how they displace after a major natural or a social event. As said, we wanted Mobilkit to be scalable. That is why we implemented using Python dask. Here on the right, you can see that on a small sample of more than 200,000 users with 57 million pings, the number of processes that we allocate to analyze this data allows to cut the computing time to a fraction of the initial one. So it's a framework that is scalable to thousands, and also if one has a machine powerful enough, millions of users, is able to process large region of interest and long-time windows. As we said, as we showed, and we will show later, it features a rich set of advanced analysis. We provide also easy pip installation via the Python package manager. And since we released on GitHub the open source, the source code, it can be easily interfaced with other libraries, for example, Scikit Mobility. So going very quickly through some example, we'll just show how the usual workflow is performed. For example, we can start with some data. We just need the pattern of the data to be loaded. And for example, in this case, since we are loading data from, for example, Mexico, we want to localize the timestamps and filter the data to be within these 2 days because we are interested in this time period. Once we load this data frame of events that is loaded by dask in lazy mode, we can compute some statistics of the users and visualize them. So, for example, the statistics that can be visualized are the number of records of recorded position that each user has, and, for example, the number of active days. If we want, depending on the analysis, we can set a minimum threshold, a minimum requirement on these 2 indicators, or on some others more complex indicators about the user activity to retain only the statistically significant users. So, for example, here we start from this data frame and we filter only users that have, for example, 100 ping and have been active for at least 2 weeks. Once we do that, we can then perform a tessellation, that is assign each recorded event to a given area of our region of interest using the spatial module again and the tessellate function, and we get a data frame with an additional column telling the zone ID of each where each to which each being belongs. Once we have that, we can, for example, compute the home and work location of each user. So, for example, if we say that we assume the user to be at home between 6:30 p.m. and 7:30 a.m. and for him to be at work between 9 and 17:30, we can compute with these two functions the location of the work and home location of the users, meaning that we know the census area where he lives in and the approximate location of this home, and the same holds for the workplace. We can then check the representativeness. For example, here in this case, we show in Mexico the representativeness at 3 hierarchical level of aggregation. If we go to the block level, of course, we don't have, we have some noise in the determination of the residential area of users, so the agreement is not ideal, even though there is a strong correlation between the census and the mobility data estimation of resident people. If we go to the upper level, which is the neighborhoods of the city, the districts of the cities, we have a better agreement. And of course, if we go to the third level of the municipality, the agreement is pretty much is really good. This allows us to do a first characterization of risk exposure, because we can overcome the limitation of the census figures on the residential of where people reside, and have a different mapping of the density during nighttime, so the home of the users, and during the day. As you can see, there are some attractors like these two universities here and an hospital that during the nighttime are completely let's say without people inside, and of course with this the usage of this by using this information, we can have a first idea of where people might be found during the day. Of course, we can then build all kinds of indicators, such as origin destination matrices, so visualize where people working in a given area come from in the morning. And also in this case here, we compare the volume of commuters as predicted by the, as detected by the census, and as inferred by our mobility data. And also in this case, we see that we have a nice agreement. Another level, an additional level of complexity about the activity, the level of presence of people in the different city areas is done by computing the activity profiles of each area. So, for example, for each area in our region of interest, we can compute using Mobilkit the volume of activity. So, for example, the number of people seen in each area for each, for example, given hour. And then I won't go through the details, but there are different ways to normalize this signal to have information where the area is getting more or less crowded during the day. The traditional way is to compute the zeta score, which is obtained by simply removing the average and dividing by the standard deviation the signal of each area. But this is not very informing, because these data have the tendency to be quite sparse during nighttime and very, let's say, abundant during the day. And so here we don't have that much of information, because all the areas are either very low, have a very low zeta score here, or very high zeta score there. So the additional step is to compute a residual activity. That means compare the zeta score of an area to the average zeta score of all the other areas at that time being, and you get the residual activity. You can do that all of these manipulations by using two functions in Mobilkit. So the first is to compute a temporal profile which is a hourly time being activity for each area throughout the day. And then you can compute the residual activity looking at the user signal over the daily profile that you just computed. And if you use the visualization tools in Mobilkit, you can see that there are, for example, in this case, 4 clusters of activity of areas that are either more active during the nighttime or during the evening, or during the nighttime, or during the day, for example, the 4th cluster here. What you did basically with these 4 steps, with these two steps, is that you detected land use. And if you map it, here it is an example in the neighborhood of Mexico City, you find different land usage in the different part of the city. So for example, here you have an area with a lot of night activities like restaurants, etc. This is the airport, which is labeled as a workplace area because it's mainly visited during the day. And then you have other parts that are more residential or more devoted to the peak hours of the rush hour in the morning. And another kind of movement that you can track using Mobilkit is displacement. Here we go in kind of into the application of in a disaster scenario. So by displacement, we mean a user that sleeps outside of his own area. So for example, in this case, we select a number of days, of initial days of warm up, where we assign a user to a given residential area by looking at the location where he sleeps the most. And then after a given event, we start tracking with some windows, the location where he sleeps the most during this window of, for example, here 3 days. And if he sleeps the most in an area which is not his original home area, we say that the user is displaced. This can be done, of course, in Mobilkit. We provide this functionality. For example, you set the number of initial days to determine the user's home, and then the width of the window to use to detect displacement, and you compute the home location window. What you get is basically for each user and for each possible window date, you have the candidate tile ID that is the one where he supposedly slept that night. If you use another function from the toolkit, you compute the displacement figures that basically tells you by comparing the home of the people and the original home of the users and the running home of the users, returns an indication of displacement. This result can be sliced or grouped in different ways. For example, here we see that during after the Puebla earthquake in Mexico in 2017, if we group users by their belonging to different areas grouped by the distance from the epicenter, we see that the distance being the area belonging to the closer distance being are the ones, of course, where you observe a stronger level of displacement right after the event, whereas in the others you don't see such a clear spike after the event. Another analysis that you can do, since you know where people have slept after the event with the window function, you can also see, for example, here a sort of origin destination of displaced people from Mexico City. You see that after the seismic event, people displaced pretty much everywhere in Mexico. Moving one step away from home, you can also see when and where people go during the day. So for example, if you define a set of point of interest to be characterized in terms of the visiting pattern, you can characterize the visiting profile and the kind of people that goes there using our toolkit. So what you have to do is to define a location of the point of interest, name and a radius. That means everything that happens 500 meters or 200 meters away from that location is to be considered part of the activity of this particular point. And then you can also categorize the point as a shelter, as a train station, as a transport point of interest, etc. If you do that, you can do that, of course, defining this this data frame of locations and defining and using this function that basically takes care of, for example, not counting the presence of a person that is close to his home as a visit to a point of interest, because we don't want to we don't have to count someone visiting a shopping center if he is actually at home. And you can compute the hourly, for example, in this case, the hourly visiting pattern to different point of interest. So you can then do this analysis for two reasons. One, if you want to detect changes in the visit rate to a given category of point of interest. In this case, we took the Dia de los Muertos in 2017 in Mexico City. We divide the visiting pattern to the cemetery areas where the festival is held and the main transport areas, so the airport and two main bus stations. And if you check the visiting pattern to these areas, you see that you have spikes right before the event and during the week of the festival, and then the signal goes back to the normal average value after that. Or you can use this analysis to, for example, characterize the kind of people that go to, for example, shelters after the earthquake. So again, about the earthquake, you can, for example, see the average wealth index of people that were close by a shelter during right after the event, and see where they were residing. So draw some insights on their wealth index. Or you can also see how far they traveled based on the poverty index of the residential area. So, for example, in this case, it was found that richer people had possibly more alternatives and likely to be far away from home there with respect to more deprived, with respect to people living in more deprived neighborhoods. There are other use cases that I will just show you very quickly because we are out of time. So, for example, you can also characterize the pattern of visit to public venues, such as public parks. These are work in progress by the GFORR. This is, for example, in Chennai, India. Or, as Bo showed before, measure the impact of COVID, of the number of commuting trips in the Kathmandu Valley of Nepal. And you can see that very quickly, if you compute the number of trips, you see that the decrease due to the lockdown and then the reopening phase here in the data quite well. So to conclude, we presented a Mobilkit, a high-performance Python toolkit to quickly and easily process data and perform all kind of advanced analysis related and useful for disaster management. Check the data representativeness and detect shift, changes, and use and displacement after major events. There are two archive publication that you can check, one regarding implementation and the other about the Mexican use case. And of course, we have future work in mind to extend the framework to support stop and trips and implement advanced expansion techniques to mitigate the biases of the data. This is the team behind the development of Mobilkit. That was a joint effort between Mindert and the GFDRR. And if you want to know more about Mobilkit, try it or read more about it, these are the coordinates. And I thank you for your attention.
Thank you very much, Enrico, for your presentation. Is there any doubts or questions from the audience? Not meanwhile, have you shared like this preliminary results with stakeholders and see how they could adopt Mobilkit for their daily use?
So we didn't directly interacted with them, but for example, internally in MindEarth, we are trying to use the part about the dynamical population mapping to interact with Italian public stakeholders to support their activity right after major natural events. But for that part, the team of the GFORR is more the one with more contacts with the stakeholders, let's say.
Perfect. Thank you very much. And there is also a question for Bo. Akash asked, did you get a chance to run the model for other cities? Would you expect the results to be consistent across large metro versus small metro areas?
That's actually a great question. So we actually have expanded this almost the same methodology for 19 different cities in the US, and that work is work in progress. So we found that most of Eastern Coast city, like Philadelphia, Washington, D.C., Boston, Chicago, the area has pretty much a similar kind of patterns as New York. But we found that a little bit different patterns in, like California or South or West cities in the US. So, but now we need to kind of like figure out like, commonality and similarity and dissimilarity of this exposure density patterns based on, similar method for different cities. Yeah. So I hope, I can share that kind of updated, new research with, within, Urban Crisis and World Bank pretty soon. Yeah. You're on mute, Andy.
Thank you. There is another question for Enrico. Does Mobilkit has its own indexing for spatial joints?
Yeah, so by now, no, because we under the hood it uses GeoPandas, and it makes a plain spatial join operation. However, since dask parallelized the work on the big data set, you end up joining only a small fraction of the data for each cycle. So it's it can be optimized in that sense, yes. And indeed, the tessellation is the most time-consuming operation of all the ones among all that I've shown. But yes, that's definitely one thing to work about.
Thank you very much. Actually, both presentations were amazing and had a lot of applications for public policy design. I'm really excited to hear about your research, and let's see how we could apply this. Thank you very much for everyone attending the meeting. Our last meeting for the year is going to be on December 16, Thursday at 9 a.m. as the usual ones. I hope to see you there. We're going to talk about data, privacy, and ethics. So thank you very much for everyone that joined, and see you soon. Happy Thanksgiving for everyone, and have a good week.
Thanks, Andy.
Thanks everybody. Bye.